So for this video, I want to talk about two effects that determine acidity and basicity. The first one is just inductive effects. So let's consider a reaction between ammonia, NH3, and water. What I like to think about in this sort of acid-base reaction is I like to think about the fact that the lone pair on the nitrogen is able to pick off a proton from the water. So the more available the lone pair is to do this reaction where it pick off a proton from the water, the more basic my nitrogen is. So this reaction goes as follows. So the more available the lone pair is, you can think about the more basic that nitrogen is. So when I look for bases in reactions, I look for things like nitrogens, phosphorus atoms, and what I'm really looking for is I'm looking for lone pairs that can accept electrons. So let's compare NH3 to something like NF3. So if I draw NF3, it looks a lot like NH3, except we have a ton of fluorines, and you can remember that fluorines are electron withdrawing, they're extremely electronegative. So what you can think about is you can think about that lone pair is sort of being pulled to those fluorines. That's making that lone pair less basic. So when we try to pick off a hydrogen atom from H2O, it's going to be harder in NF3 versus NH3. And the reason behind that is because of an inductive effect. So in this example, NF3 is less basic than NH3. Why that is, again, is an inductive effect. We're decreasing the availability of this lone pair. So this lone pair is not as available to pick off that hydrogen in water. So that's one example of an inductive effect in terms of basicity. A classic example of an inductive effect versus acidity is when you compare things like, let's say we have acetic acid. Let's compare that to trifluoroacetic acid. Keep losing my lone pairs. Let's compare acetic acid to trifluoroacetic acid. So it turns out trifluoroacetic acid is actually more acidic than acetic acid. So this is trifluoroacetic acid, this is acetic acid. So why is that? Well, one way we could think about this is we could think about the inductive effect. So the fluorines are all sort of pulling on this carbon right here. They're pulling away electron density, and that inductive effect is felt throughout the molecule, and what that's doing is that's actually weakening this OH bond right here. So you could think there's sort of a net pull in the molecule to the fluorines. that weakens this OH bond right here, and that makes this proton more available to interact with other things. So since that bond right here is weakened, this proton is more acidic. So trifluoroacetic acid is more acidic than acetic acid. This is another example of an inductive effect. So the last type of effect I want to talk about is what's called a steric effect. So imagine let's say I have 3 different nitrogen heterocycles. So I have pyridine, and then let's imagine I have 2 different types of picoline molecules. So picoline is just essentially pyridine with a methyl group on it. And let's say we want to rank these in terms of basicity. So one thing to recognize is that we have a nitrogen with a lone pair on all of these molecules. This is sort of my tell for when I have a base. I have a nitrogen with a lone pair that's available. So let's compare these molecules. So the difference between the pyridine and the picoline molecules is this methyl group right here. So what's interesting is, okay, this methyl group is actually inductively donating. So a methyl group is donating. So a methyl group can donate electrons into the ring. That makes this nitrogen lone pair more available when we have a methyl group here. But in the case of when we have a methyl group in the 2 position, what happens is that has a steric constraint. So this methyl group right here is able to block an incoming hydrogen. So the methyl group in the 2 position is able to block an incoming hydrogen. And what the effects of that are is that something like 2 picoline versus pyridine and 4 picoline, this is the least basic. 4 picoline in this series is actually the most basic. This comes from that inductive effect. And note that the methyl group right here is far enough away from the lone pair on the nitrogen to interact. And then sort of the intermediate case is the pyridine. So this is the steric effects. So a lot of times you'll see molecules, like let's draw another example. All right. Alright, this is ditert-butyl-pyridine. This molecule has a lot of steric hindrance because of these large T-butyl groups, and that's going to really prevent this nitrogen from being protonated. So here's another molecule where sterics comes into play.